All right, good morning, everybody. I hope you guys all had a great Monday, Tuesday finally, Tuesday already, I guess. Okay, so a couple of things before we get started. Yesterday, I gave you feedback for assignment 9. I'm still disappointed when I go in to provide the feedback at how many people have actually gone in to complete these assignments. So they are few and far between for this class specifically. So please take the time. I cannot stress this enough that the more practice you have with these type of problems, the easier they will become. And the problems that I choose for the assignments are very specific to final exam level questions and things you could expect to see. So if you're doing these problems, that gives you a way better chance of success. So please take the time to go in and do these problems. Couple of other things. I was asked for some extra practice on radicals and rational expressions. So last night I posted a couple of extra worksheets with the solutions. So if you need some extra practice, they're there, but make sure you're doing all the sheets as much as possible, okay? So that should just be extra practice, but you should take the time to go in and do the handouts that I gave you and the assignments that I gave you. Don't forget that if you do the assignment, even now you can go in and complete the assignment. As soon as you hit submit and turn in, I get a notification that your assignment was turned in. So you really have to make sure to hit turn in. And if you do that, then I still get a notification that you've turned it in, which means I can go in and still give you feedback. Even if it's assignment 1, 2, 3, doesn't matter. I can go in and give you feedback on that. The other thing that was posted yesterday was the the CITPROB updated list. So this was a list that just narrowed down the topics. That way you weren't overwhelmed with studying for the situational problem. I do remind you that all the topics on the course outline are fair game for this final exam, but I wanted to give you a little bit of a narrower scope for the CITPROB. That way it wasn't too overwhelming. There's a question in the chat already. It says we need to know proportions for our CITPROBs. Proportions is something that you do in secondary 2 and 3 and 4. You use it all the time. We actually used it yesterday, just setting up our proportional relationship. We did it using probability. So it's just being able to set up some sort of proportional relationship to solve for a missing value. So you do start that as a secondary 2, and then you use it as a skill every year. You just don't say this is a proportion. Okay, so you should have the skills to be able to do that. So just general reminders about the CITPROB before we get started. It's tomorrow, 8:30 sharp. You'll have exactly 2 hours. Bring just what you need, what you're writing with, your calculator. I won't have any extras, so do not forget your calculator, and you will not be allowed to use your cell phone. The classroom is 334. You are allowed a memory aid, double-sided, as per usual, handwritten, and I will be checking memory aids tomorrow. So if they're typed, I will be taking them away. So don't make that mistake, please. Yes, you can have, like I said, yes, you can have the double-sided memory aid, but you should also be thinking about prepping your memory aid for the final. And so that should be a thought in your brain as well. So you shouldn't, in theory, need both sides just for this CITPROB, but if you want to use it, feel free. Are there any questions about the CITPROB? Because that's super important. That's a huge chunk of your grade tomorrow. A big enough chunk. Okay, I guess we're all set. If any questions pop up about the CITPROB, you can just ask me throughout the class or whatever you need. Before we get started, are continuing on the material, are there any questions about any of the assignments, any of the handouts? Now would be the time. So I'm going to open up the lecture, but while I'm doing that, take the time to post on the chat if there are any questions that you saw that you'd like to go over, or take a quick minute just to look at some questions to make sure that you would be able to handle them. Yes, so the question is, the only thing that is being graded are the 2 exams. Yes, so you have, if you remember the breakdown that we looked at, your sit prob tomorrow is going to be worth 30%, and the final, the ministry final, which is on the following Tuesday on the 25th, will be worth 70% of your grade. So there's no other grades coming from there, just the 2 exams. Class 12 notes were posted yesterday. Were they not posted yesterday? Well, that's weird. Guys, if I ever forget, you just send me an email. Sorry about that. They were ready, all ready to go. I thought I posted them. My mistake. Make sure both groups get it. Just in case. There we go. So sorry about that. If you ever see that I do that, I mean, there's only one left in reality, but if I do it again, which is very unlikely, but if it does happen, just feel free to send me an email or to just post to Google Classroom, because chances are everything's ready to go. I just probably made a little brain mistake, that's all. You could take a minute to print the notes. We're still on class 11 though. We still have some stuff to finish up there, but you could take a minute to print the notes for sure. I was just asked to do number assignment 11, number 2. So I'll just set up for that problem while you guys are printing out the notes. Are we just about ready? Sure. In the meantime, if there's anybody else that has, if you're not printing out your notes and you do have questions that you want to go over, please take the time to post them on the chat, because if not, I'm just going to keep going with the notes when we're ready to go after this problem. Okay, so I'll get started unless there are any objections. Okay, cool. So assignment 11, number 2 says, a travel agency would like to know what language the people taking their tours are capable of speaking. The survey reveals the following results. So we have people that are speaking in French. So we have French, we have English, and we have Spanish. So we have 3 different variables here. So in my Venn diagram, I'm going to make 3 circles. French, English. I think I did a reverse on my answer key, so just to be consistent. Spanish. It really doesn't matter. English, French. So now what we're going to do is, you see we have several overlaps. So here is the overlap between English and French. Here's the overlap between English and Spanish. Here's the overlap between Spanish and French. And this is the overlap between the 3 of them. So based on the information that we're going to get, we're going to be filling some stuff in. So 6 people can communicate in French, English, and Spanish. 6. 38 people can communicate in French. But we can't put that into the French thing because the French is going to be put together of this, 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 and this. So we're just going to put French. Here is 38 so that we know. 10 people can communicate in English and in French, but not in Spanish. So English and French, but not Spanish. So that goes in the overlap of English and French. Assignment 11, number 2. "20 people can communicate in Spanish only." So that goes in the Spanish only portion of the Venn diagram. 8 people can communicate in French and Spanish, but not English. So that goes in the overlap of French and Spanish. 12 people cannot communicate in any of these languages, so they wouldn't fall in there. They would fall outside the Venn diagram. We know that there should be 38 in this circle. So we can just take 38 minus 10 minus 6 minus 8. And that gives us 14. So there's 14 people that can only speak French. The probability that a person cannot communicate in, so we're going to jump. The probability that a person cannot communicate in any of the languages equal to 1 over 8. Okay, so we know that 1 over 8, we know that there are 12 people that can communicate in none of these languages. We need to know how many people there are total. So this is an example of a proportion. So x is 12 times 8. X is 96. So in this whole Venn diagram, I should have 96 people. So I'm missing 2 things here. So I'm just going to figure out how many people I'm missing. So there are 26 people that need to go in here. When a person can communicate in Spanish, the probability that they can also communicate in English is equal to 5 over 19. So this one's a little trickier. Just take a look here. Did I mess something up? Did I not use that at all? 5 over 19. Probability is not on the sit prob. We're not doing trigonometry together. SOHCAHTOA, sign law, and area. Okay, we're going to save this problem because you need a tool that we haven't actually covered yet. We're going to be covering today, so we can come back to this problem. Okay, so for now we're going to put a pin in this because to figure out this thing here, we can't do this yet. We need what we're doing today. So yes, SOHCAHTOA and sign law and area formula, so Hero's formula and the other area formula are fair game for the final, but we're not covering it together because everything that you covered throughout the year You've already covered all of trigonometry throughout the year. Nothing is different. Actually, there's a bit less, so you actually know more than you need to right now. So what I can do is I can post this week at some point some just refresher notes if you want, but we're not actually taking the time to cover it in class because that's part of the list of stuff that you should already know. Okay, so like I said, we're going to put a pin in this problem. We're going to continue where we left off, and then we'll come back probably at the beginning of Thursday's class to this problem. So we did a lot of Venn diagrams yesterday and a lot of different definitions and stuff, and we talked about our laws of probability. But what are we doing with this? Okay, so first we're going to look at some problems that we can do, and then we're going to look at the tools or the specific thing that we're going to be using Venn diagrams for. So when we are doing a problem, just like the one before, except we're missing a tool as of now, you set up the Venn diagram, and from the information given, you set up the relationships. You fill in the known information, you calculate the known information, calculate the unknown information, and then get the probability that you need. So let's see what this looks like. There are 200 students that had to write an English and a math exam. 60 students passed both exams. 48 students passed math but failed English. 20 failed both exams. What is the probability that a student passed English? So what I'm going to do is I have this Venn diagram already. I'm going to call this passed, or here, we'll just do this on the side. A will be passed math. And B can be passed English. So I'll put B in this one and A in this one. And this is my universal set. So it says that there are 200 students total. I can't use that yet. 60 students passed both exams. So 60 goes in the intersection. 48 passed math but failed English. So 48 would go in here. And 20 failed both exams. So if I know that this part and this part and this part and this part should add up to 200, all I have to do is take 200 minus 48 minus 60 minus 20. And that will give me the number that passed English but not math. So 200 minus 48 minus 60 minus 20 gives me 72. So there are 72 people that passed English and nothing else. The question asks me, what is the probability that a student passed English? So probability of passed English. So we remember that we have the number in the English. So we have everything in the English circle. So I'm going to take 60 plus 72. That gives me 132. So there are 132 students that passed English out of the 200. So you can just reduce this. And that gives me 0.66, which is the same as 66%. So 66% of students passed English. Good? Okay, let's take this time to do another one. There are 50 tourists on a bus. 20 speak Spanish, 28 speak English, 10 speak both languages. Find the probability that a person speaks English. I've said this before, but if you did probability in secondary 5, if you've already passed your Sec 5 CST, the probability units will be similar. So you'll probably have done most of this already, what we're doing today. So we have English speakers, so we'll say English and Spanish. So I know that 20 speak Spanish, but that's the whole thing here. We don't really need the Venn diagram to answer this question, but we're going to do it anyway. 10 speak both languages, so that goes here. 20 speak Spanish, but there's already 10 here, so it's only 10 that go here. 28 speak English, but there's 10 here, so we only need 18. What that leaves me with for the outside is 50 minus 10 minus 10 minus 18, and that leaves it on the outside. So there are 12 people that don't speak either Spanish or English. So the probability of English, which, like I said, we really didn't need to answer this question, but we can just do it anyway. So here we get 14 over 25. Which, if you want, you could write it as 0.56 or 56%. Really doesn't matter. I know it's 28 for English, but English is this entire circle. So when I put the 18 with the 10, that means 28. Because you always have to remember it's the whole circle for English. So here there's 18 and here there's 10. Okay. Let A and B be two events such that the probability of A is 0.7, the probability of B is 0.5, and the intersection is 0.4. Make a Venn diagram that represents this situation and find the probability of A or B. So even though we have probabilities, we are just going to fill in the numbers as per usual. So we always start with the intersection. So we have the intersection, which is 0.4. Because from the intersection, we know how much is left over in just A. So A is going to be 0.7 minus 0.4, which is 0.3. So on the outside here, we have 0.3. Remembering that this together gives me the 0.7 that makes up all of A. And then I'm going to do the same thing here, 0.5 for B. 0.5 minus 0.4 leaves me with 0.1, that's just in B. And if I wanted to know, remembering that probability adds up to 1, so 1 minus 0.3 minus 0.4 minus 0.1 gives me 0.2 that goes on the outside in the universal set, but not included in the circles. Now we also remember that this means this whole thing. So the probability of A or B is going to be these three numbers added up together, which gives me 0.8. So notice that I can't just take all these numbers and add them up. Because if I take all those numbers and add them up, I'm going to get something bigger than 1. So to really see what's in what part of the Venn diagram, you have to actually construct the Venn diagram. Does that make sense? Are we feeling okay, or do you want to see one more? Okay. You are asked to draw a card from a 52 card deck. Let A be drawing a face card. And B be drawing a spade. Make a Venn diagram to represent the situation and find the probability of drawing a face card, a spade that is not a face card. So this gets a little trickier because you can't just plug it in, you have to think. How many face cards are there? Well, I've got 4 jacks, 4 queens, and 4 kings. So that means there are 12 face cards. How many spades are there in the deck? 13. How many face cards that are spades? Well, out of the 12 face cards, we've got 1 jack of spades, 1 queen of spades, 1 king of spades, so there are 3. So there's 3 in the intersection. If there's 3 here, that leaves me 9 here on the outside. And that leaves me 10 here on the outside. And if we wanted to just finish this up, I would take the 52 minus 9 minus 3 minus 10. And that would give me how many cards are on the outside. That gives me 30 on the outside. So in a standard deck of cards, you have the numbers 1 through 10, and then you have a jack, a queen, and a king. So the J, the Q, and the K, those are called face cards. Remember, there are 4 of each card. And for each card, for every ace, there's a spade, a heart, a diamond, and a club. So now the question is asking, find the probability of drawing a spade that is not a face card. So we have probability of spade that is not a face card. We have 10 of those over the 52 total. So 10 divided by 52. If you just want to reduce this fraction, just gives you 5 over 26. The decimal's not really nice, so you don't have to put it in. Any other questions? Okay. What are we doing this for? We are doing this for a specific thing called conditional probability. So conditional probability, we have 2 things that are happening, 2 different characteristics or 2 different events. And we want the probability that event A occurred given, so this word given is super important because 90% of the time the problems are actually going to say the word given, and you need to know that that is conditional probability. So it's the fact that we know that event B occurred. What is the probability of A occurring? So here, this line symbol means given. So what this means is A given B occurred. So there are 2 different ways of calculating this. Either you take the number in the intersection and then the number in B total, or you take the probability of the intersection and the probability of B total, and you divide them, and that is your conditional probability. We're going to do two different types of conditional probabilities. It's the same calculation, but depending on how the information is presented to you, either you're going to use a Venn diagram or you're not. And they're often, this is a part A question, often. So your first thing you're going to do is fill out the Venn diagram based on the information you're given. So we have a group of 25 students. So we're going to pass the English test E and pass the biology test B. And then we're going to fill out the Venn diagram completely. So we have E, we have B here, and we have E here, and the universal here on the outside. So we have 12 passed both tests. So we have 12 in here. 16 passed biology. So there are 4 left over. Since there's 12 already here, there's 4 left over to go here. 18 passed the English, which means there are 6 left over for me to put here. And then for the outside, I have 25 minus 6 minus 4 minus 12. And that gives me 3 that failed both tests. So the questions are going to look like this. Find the probability that the student passed English given that he passed biology. So there's going to be something that we know about this person. So we want the probability of English given that he passed biology. So we're going to use the number one. So we have the number of the intersection between them and the number of just biology. So the intersection between them, that's this middle part. And the number in biology is the number total, 16. So we just divide, and this gives me 0.75. At Central Academy, there are 20 students in a physics class. 18 students pass their optics test, 15 students pass their mechanics test, and 15 students pass both their optics and mechanics tests. What is, I can go up again, please, sure. Okay, so it's a good question. Do they want a fraction? Any of these are acceptable answers. But if you get this as a multiple choice question, you don't have a say in how the answer is going to be presented. So it could be presented as a fraction, it could be presented as a decimal, it could be presented as a percent. So you just have to be comfortable converting one to the other to be able to solve. If for some reason you get this as a part B question, then any of those answers will be acceptable because they all represent the same thing. So this one and this one and this one will all be accepted. Okay, so we've got the optics test. And we've got the mechanics test. So we're going to fill out our Venn diagram. 18, we just care, first we care about the intersection. So 15 passed both. How many passed the mechanics? 16, so there's only 1 in here. And 18 passed the optics. So there are 3 in here. And we have 20 students minus 3 minus 15 minus 1. That gives me 1 left over here in the universal set. Just change this is to given. So what is the probability that a student passes their optics test given that the students pass the mechanics? So we have the probability of optics given that they pass their mechanics test. That gives me the number of the intersection divided by the number of mechanics. So the second one goes on the bottom as well. So the intersection between them, there are 15. How many total passed mechanics? 16. And that's done. You could convert this, like I said, to a percent, but you don't have to. Can I continue? I'm going to take that as a yes. At a college, 70% of students passed English, 60% passed French, 50% passed both. Find the probability that a student passed French given that they passed English. Same thing. English, French. So you always start with the intersection. This is not on the exam tomorrow. You start with the intersection, 50%. We have 60 passed French. So that means that here there's 10 left over that passed French only. 70 passed English, so that means there's 20 left over here. And in the universal, we'll have, it's 100% minus 20, minus 50, minus 10. That leaves me 20 that didn't pass any of them. So we want, find the probability that a student passed French given that they passed English. So we want the probability that the student passed French given that he passed English. So we have the number of the intersection. So we have F intersection E. And the number of E. So I have 50 over E, which is 70. So that reduces to 5 over 7. So the comment or question is that these are percentages, not numbers. Yes, so there are different ways that you could do this. If you wanted to put these as percentages, you could also just, percentages are just decimals, right? So it's the same idea. You would have the same calculation here, except you'd have decimals. So you'd have 0.5 over 0.7, which if you do that on your calculator, gives you 5 over 7. So because it was a percent, I could put it as a whole number or I could put it as a decimal. And in the end, because I'm doing a probability, as long as I'm consistent, it didn't really matter which one I used. Does that make sense? How do we feel about this conditional probability? Not too bad. Okay. So that was conditional probability using Venn diagrams. There's a different tool that we can use to calculate conditional probability, and this is the one you're more likely to get. Like, this one comes up on the final a lot. Like I said, every time I talk about the final, I have no idea because I don't make it. I have nothing to do with it, and I see it after you see it, but you kind of see what comes up. So chances are you'd be given, like, you'll probably be given the entry table, but if you're not, you have to set up the table. So we'll take a look at the examples of setting up a table. So you have two or three actually, different kinds of variables that you'll be looking at. So in an entry table, you're going to have one, either like let's say the length, the columns, I guess, will be one variable and the rows will be another type of variable. And then you end up with intersection between them. And you'll fill in your numbers. And from there, you'll be able to do the conditional probability calculation. This is the next page from here, the next page over. So here we have a middle school in Chicago has 400 students. We have girls. So what we are going to be doing is our last column is always total. I see that they're talking about girls and boys. They're also talking about grade 7, grade 8. Now, how we will read this is going to be the total number of girls. This will be the total number of boys. This will be the total number of grade 7. This will be the total number of grade 8. This number will be the girls in grade 7. This number will be the girls in grade 8. This number will be the boys in grade 7, and this number will be the boys in grade 8. And this is the total number of students, which is 400. So what I'm going to do now is I need to fill out these values. So I am told that there are 240 girls. So boys are going to be 400 minus 240. So there are going to be 160 boys. I'm going to write this in blue. %70 of the students are in grade 7. So if I take 0.7 times 400, 0.7 times 400, that gives me 280 in grade 7. 400 minus 280, that gives me 120 in grade 8. So here, we're just going to change this boy, grade 7 boy. So the probability of selecting a grade 7 boy at random is 1/4. So if I take 1/4 of 400, that gives me 100. That is how many grade 7 boys I have, 100. Well, now I can fill out these ones. If there are 100 boys in grade 7, that means there are 60 here. If there are 60 here, there are 60 here. And that means there are 180 here. So this is how you fill in a double entry table. Now I could ask you, let's say, what is the probability of selecting a girl given that she is in grade 8? Well, this is the number of girl grade 8, the intersection of them, divided by the total number of grade 8. So what is the intersection of girl and grade 8? Well, girl and grade 8 is 60. How many grade 8s are there? There are 120. So this is 1/2 or 50%. Tomorrow is a situational problem. That's why I keep saying SIPROB. It's a situational problem. The one you had in CST is like the one you have on Tuesday of next week, obviously. Because today is the Tuesday. All right. Let's do another one. In a class of 30 students, 3/5 are boys. The probability that a student chosen at random is right-handed is 4/5. The probability of selecting a right-handed girl at random is 1/3. If a boy is selected, what is the probability that he is left-handed? So our first move, we have to fill out our table. So again, we're talking girls and boys, and we have a total. And here we have right-handed and left-handed. So you're always looking at two different types of variables when you're doing a double entry table like this. So you're looking at, first you looked at girls versus boys, and you're looking at right-handed versus left-handed, and you have total. So you have that there are 30 students. So 30 is your total. So now based on the information, you need to figure out how to fill out your entry table. So 3/5 of the students are boys. So if 3/5 are boys, we multiply 30 by 3/5. And that gives us 12. No, it doesn't give us 12. What am I talking about? I guess it's 18. So there are 18 boys. 30 minus 18 gives me 12 girls, right? Because these two add up to give me this total. What other information do I have? The probability that a student chosen at random is right-handed is 4/5. So 4/5 times 30 gives me 24. So that is how many are right-handed, meaning that there are 6 left-handed kids. The last probability, the probability of selecting a right-handed girl at random is 1/3. So we have 1/3. That gives me 10. That's a right-handed girl. So that goes there. Now I can fill out the other ones. Because there are 12 girls, 10 of them are right-handed. That means 2 are left-handed. There are 6 people that are left-handed, 2 are girls, so 4 are boys. 18 are boys, 4 are left-handed, 14 are right-handed. If a boy is selected, what is the probability that he is left-handed? So probability of being left-handed given that you're a boy. Because it's telling you that it's a boy that's selected. So that is what is given to you. We know that it's a boy. What do we want to know? The probability of left-handed in that case. So we know that this is the number of the intersection between them and the number of boys. So how many left-handed boys are there? There are 4. How many boys total? There are 18. So this is 2/9 or 22.2%. So the question is, why don't I do 1/3 times 24? Because it didn't say that it just said the probability of selecting a right-handed girl at random. That's from the whole group, not just from the right-handed kids. So the probability of selecting a right-handed girl out of the whole group was 1/3. So we did 1/3 times the amount for the whole group. Let's do another one. There are 200 students in grade 10 at Random High School. The probability of selecting a boy at random is 60%. 20% of the 200 students speak French, the rest speak English. The probability of selecting a French-speaking girl at random is 15%. So before we even look at the question, like given this, find this, we're just going to fill out the table because we can't do anything without the table. So we have girls and boys, and we have French and English. So those are the 2 things that we're working with, and we have our totals. And we know that the total number of students is 200. So the probability of selecting a boy at random is 60%. So 60 out of 100 times the 200, that gives me 120 boys. So if there are 120 boys, there should be 80 girls. "25% speak French. So 25 over 100 out of the 200 gives me 50 that speak French and 150 in that case that speak English. The probability of selecting a French-speaking girl at random is 15. So 15 over 100 times the total of 200 gives me 30. That's a French-speaking girl. From there, I could figure out the rest. So if 30 of the French speakers are girls, there should be 20 that are boys. If 30 of the girls speak French, then 50 will speak English. If there are 120 boys and 20 speak French, there are 100 that speak English. Once my entry table has been filled out, we can look at the question. If a girl is chosen at random, so we know that it's a girl, she's a girl, what is the probability that she speaks English? So we want the probability of English given that we know it's a girl. So again, that's the number in the intersection and the number of just girls. So English girl, we have 50 out of 80 girls. So this reduces to 5/8, or you could write it as 62.5%. How do we feel about conditional probability? Do we want to do one more example, or we feel comfortable? Any takers on the one more example? Okay, one more example is going to come from the handouts. So the handout I gave you yesterday. Open with. Go to number 11. During the last census at a retirement home, some data were established and represented in the following table. A resident is chosen at random. What is the probability that this person is between 80 and 85 years old, given that this resident is a male? So your first step, if you see in some of the problems, the previous problems, the entry table is filled out for you. So this is an example of a type of Part A question. So you're really happy because you don't even have to fill out the table. But chances are you're going to have to fill out a table. So here we have, they gave us the table though, that was nice. So here we have blank spaces to fill out, but it's not too bad for us to fill out. So here we have 400 minus 175. That gives us 225 here. We can fill it out whatever order you want. 35 and 45, so there's 10 that should go here. 20 and 80, there's 60 that should go here. If I take this 400 minus 130 minus 80 minus 45, that gives me 145 here. Whatever you want. 130 minus 75 gives me 55 here. 175 minus 75 minus 20 minus 10 gives me 70 here. So that gives me 75 here. You can check your answers. What is the probability a resident is chosen at random? So what is the probability that they are between 85 and 80, given that this resident is a male? So the probability of being between 85 and 80, or 80 and 85, given that you're a male. So that's the number in the intersection. And the number of just males. So the number in the intersection would be the 75. And the number of just males is 225. And then this can be reduced to 1/3, or 33.3%. Any questions on that or on conditional probability? So yesterday's handout and yesterday's assignment. So yesterday's handout. Did I write 226? I didn't write 226. I wrote 225. Sorry, I just kind of curled it up a little bit too much. Yesterday's handout, all of these problems here are all conditional probability except this one. That's an odds one, just to throw you another one in there. So in these cases, you're given the table. In number 9, number 10, for instance, you're not. So you have to go over these. These are really what you could expect on the final, and these are just some extra practice for Venn diagrams and conditional probability that you can do. So all of that is available. You had that yesterday, and the assignment. So on the forms, now this question is conditional probability. This is conditional probability, and this is conditional probability. So that gives you some practice there, as well as this. This is conditional probability, but you have to create the table, and so is this one. Except this one you have to think a bit more. Okay, so that's conditional probability. So I'm hoping this one goes up to like 10 by Thursday. Any other questions? Cool. Now we're like, yes, I hope I get this as a part A question on my exam, right? That's what I thought. So we have two baby things to look at for probability. And then we have one probability concept that almost always comes up as a part C question. So we're going to do a lot of practice on that. So we are now on notes 12. All right. We had these relationships, okay? We had the probability, excuse me. Of course, you're going to be a giant pain today. Thank you. This is not the last topic. We have a little thing in statistics to look at. So a lot of this, everything in statistics that you did in CST comes back. So the mean deviation, I just have to check, but percentile doesn't. But mean deviation, the correlation coefficient, the Mayer line, the comparing the correlation coefficients, the scatter plots, and the contingency tables. So all of that comes back, and then there's this added thing that's kind of like mean deviation. So you know with mean deviation, you made the table and calculated your mean deviation that way. So there's something else to do like that. And we'll be doing that on Thursday. Like I've said, the only thing that is on the SIBProb is the things on the list I posted yesterday. We're not even going to look at statistics today. So that stuff, anything that is on the list is on the SIBProb. If it's not on the list, it's not on the SIBProb. Okay. All right. So hopefully this works this time. Before, right now with conditional probability, we were working with this relationship. A given B was the probability of the intersection and divided by the probability of B. So I could just rewrite this. If I wanted to solve for the probability of the intersection, I could just rewrite this by moving this up and saying the probability of A given B times the probability of B will give me the probability of the intersection. So it makes sense, right? Like all I'm doing is taking the equation that I just worked with and manipulating it. I just moved one thing, mathematically legitimate. So we have the same thing here because we have the probability of their intersection, but this time we'll have the probability of A at the bottom. And same thing, this just kind of moves up. And we'll get the probability of the intersection. So those are just two formulas that we can apply in different problems. So this is just an inverse or a different way of using conditional probability. For example, in a factory where bolts are made, a machine M provides 40% of the total production. 10% of bolts produced by machine M are defective. A bolt is chosen at random. Give the probability that this bolt is defective. So if we call M machine M, and we call D bolt is defective, we now have to understand what these two numbers represent. So the 40% means the probability of machine M is 40% or 0.4. 10% of bolts produced by machine M are defective. Okay, so that would be the probability of defective, given that it comes from machine M, would be 0.1. So we want the probability that it comes from machine M and is defective. We want the probability that it comes from machine M and is defective. But we just had our new rule. The probability of machine M and defective is going to be the probability of defective given machine M times the probability of machine M. So that's what comes from here. Notice we have the A with the A and the B with the B. So in this case, we have the M with the M. And all we have to do is plug this in. So here we have, or here we have 0.1 and 0.4. So that gives me 0.04. So we're not going to spend too much time on this because we don't usually get questions like this. But the important thing to notice from this question is you have to really understand, the biggest thing with these type of problems is that you really have to understand what the information is that they're giving you. So I had to identify what the 40% represented and what the 10% represented, and then what they actually wanted. And once I did that, I could do my calculation. Okay. So we're just going to take a look at what it means for events to be independent. So when we're looking at conditional probability, we are assuming that there is some intersection between events, because we can't do this if there's no intersection between the events. If there's no overlap, they're called independent. And if there's no overlap, the probability of their intersection, A and B, is just the probability of A times the probability of B. Okay? If they are independent, that means that B is not going to influence A happening. So if there's no overlap, I could say, what is the probability of a boy, or what's the probability that a student has blue eyes given that they are a boy? But if there are no boys with blue eyes, it makes no sense. Or if I say, what's a kind of like really crazy example? I throw a die and I toss a coin at the same time. And my one event is rolling a 6 and my other event is getting tails. Well, whether or not I roll a 6, that's not going to influence whether or not I get tails. Those two things do not influence each other whatsoever. So they're called independent. So what is the probability of getting a tails given that I rolled a heads, given that I rolled a 6? Well, it's still just a half, because that 6 has nothing to do with my heads or tails. So we'll take a look at just some independent events. Okay. A bag has 20 marbles, red marbles, and 30 blue marbles. You draw a marble from the bag, then draw a second with replacement. Find the probability of obtaining a blue on the second draw. So I pick out a marble and I put it back in. So in this case, the probability of blue is 30 over, we have 50 marbles in the bag. And the probability of red is 20 over the 50. But I put the marble back in. So I take a marble out. I look at the color. It's blue or red. I don't really care. And I throw it back in the bag. What is the probability of obtaining a blue on the second draw? Well, there are still 50 marbles in the bag. There are still 30 blues. So my probability is still 30 over 50 because I haven't done anything. The first draw does not influence the second draw. So they are independent of each other. So it doesn't matter what I get on the first draw because I put that marble back in. They don't influence each other. The two steps, the two different things, do not influence each other. So they're independent. We're doing tree graphs in a second. A die is rolled at the same time a coin is tossed. Event A is the die shows 6, and event B is the coin shows tails. Events A and B are independent. And we'll just not take a look at this for now. Because the two events, I roll a die and I flip a coin and I look. The fact that I get a 6 has nothing to do with the fact that I get tails. Nothing to do with each other. So this is just what probability has to do when things are independent, meaning they don't influence one another. So we're going to take a look at that further. We're going to be using independent events when we're doing our next big thing with probability. Before we do that, we are going to practice constructing tree graphs. Tree graphs are something you see in secondary too, but these could be useful for you with the stuff that we're going to be doing next. So we're going to take a look at reviewing these. Tree diagrams are used to represent situations with multiple steps. So rolling a die and flipping a coin, that's two different things. Even if you're doing them simultaneously, you're doing two different steps in the sense that you're doing two different things. So to construct a tree diagram, these are a lot of steps, but they're actually straightforward when you're doing it. So you're going to place the starting dot. From the starting dot, you're going to extend a branch for each outcome of the first step. And then at the end of the branch, you write what the outcome is. I do know the Monty Hall problem. We're not going to cover that. We don't have time, but I do know it. On the branches, we're going to write the probability for each of those outcomes. From each of our branches, we are then going to extend a branch for every outcome except in step 2, finishing with the outcome, and then we put the probability on the branches. And then we keep repeating this pattern until we run out of steps. All right, so let's take a look. View. So we're going to draw a tree diagram for this situation. We'll say we have 10 red and 5 blue. So we start with our starting dot. 2 balls are drawn successfully from a jar without replacement. So that means we have 2 steps. And for each of the 2 steps, we have 2 outcomes. So for the first step, I could either get red or I could get blue. So I could get red or I could get blue. What is the probability of me getting red? Well, it's 10 over 15. And the probability of me getting blue is 5 out of 15. So we write the probability on the branches. From each of these outcomes, we extend a branch representing the next step. So for the next step, I could still get red or I could get blue. I could still get red or I could get blue. Now, without replacement means I don't place this marble back in the jar. So when I do the second pull, I only have 14 marbles. If I've already pulled out a red, there are only 9 for me left to pull from. But if I've pulled out a red, there are still 5 blue. Following this branch, if I pulled out a blue, there are still 10 red for me to choose from. And if I pull out a blue here, there are 4 left for me to choose from. From there, what I do is I make a table where I say outcome and probability. So I follow the branches. So here I get red, red, Here I would get red, blue. Here I would get blue, red. And here I would get blue, blue. What is the probability of each of these things? Well, I multiply the probabilities on the branches. So red is 10 over 15 times 9 over 14. So that gives me 90 over 210. Following this branch, I get the red, which is 10 over 15, and the blue, which is 5 over 14, which gives me 50 over 210. Blue, red gives me 5 over 15 times 10 over 14. So that gives me 50 over 210. Finally, I get blue, blue, which is 5 over 15 times 4 over 14. And that gives me 20 over 210. And all of these columns, this column here should add up to 1. So 90 and 50 and 50 and 20 adds up to 210 over 210, which is 1. So that's how we construct a tree diagram. Let's take a look at one more. You draw a card from a deck, and we're looking at the suit, and we're flipping a coin. You can simplify, and you should simplify. But when you're checking to see if they add up to 1, it's easier to leave them like this. Okay. So you draw a card from a deck, and we're checking the suit, and flip a coin. So we have step 1, we have 4 outcomes, and step 2, we have 2. So we have our starting point. From the start, I could have 1, 2, 3, 4 different outcomes. So I could have hearts, diamonds, spades, and clubs. The probability of me getting a heart is 1 over 4. The probability of me getting a diamond is 1 over 4. Spade is 1 over 4. And club is 1 over 4. Make sure this is a club. From each of these outcomes, we're going to extend a branch for our next step. So our next step has 2 outcomes. So we've got we're going to say a heart. So we've got heads and tails. And then each of these probabilities is 1/2. So then I make my table of outcome and probability. So here I get head, heart. Here I get head, tails, diamond, head, diamond, tails, spades, head, spades, tails, clubs, head, clubs, tails. So now we do each of the probabilities. So we follow the branches. So this is 1/4 times 1/2, which is 1/8. Same thing here. We get 1/4 times 1/2, which is 1/8. In this case, they all end up being 1/4 times 1/2, which is 1/8. But like we saw earlier in the previous problem, it's not necessarily the case that they'll all end up with the same probability. It just depends on your situation. In this case, we have the situation in which they have all the same probabilities. And you check to make sure that all of these probabilities add to 1, sum to 1. Do we all remember how to do tree diagrams now? Are we all more or less comfortable with them? The focus, like I said, the focus is not going to be on the tree diagram because you do cover this as a thing in secondary too, so that's not going to be the focus, but this could help you do what we're going to be doing next. So you may have to use that as a tool. You may not, but you may. So what are we going to be doing next? So this, what we are about to cover, like I said, is what is likely to come up as a Part C question. So a random variable, just for terminology's sake, is each outcome of a random experiment. So we talked about random experiment is an experiment where I can't predict the outcome. Like I know what the outcomes could be, but there's no way for me to know, is it going to be heads or is it going to be tails? Or if I roll a die, is it going to be a 1 or a 2 or a 6? I have no idea. So what we are going to be doing is we are going to be assigning, we're going to group the random variables, assign values and probabilities to them. So essentially what this is used for is playing different games, arcade games, casino games, fair games, you know, like the traveling fairs outside. So we are going to be taking outcomes, assigning values to them, and calculating the mathematical expectation based on that. So what a mathematical expectation is, it is basically when we play some sort of game, when we do some sort of big experiment, we'll call it an experiment, but basically it's always presented as a game. What is the expectation? What is the value that we expect to get on average if we play the game enough times? There are 3 different cases for the mathematical expectation. If your expectation is 0, that means on average, you would expect to get 0. The game is fair because then you have an equal amount of chances of winning money, because this always involves money, winning money or losing money. If the expectation is positive, that means on average, we expect to receive positive money as the player, which means the game is favorable to the player. If the expectation is negative, you don't want to be playing that game because on average, you expect to be losing money. So it's not favorable to the player. So we are going to be calculating the mathematical expectation of different games. To do this, we are going to be making a table every single time. So for all the examples that we're going to do, we'll probably get to 1 today. All the examples that we are going to do, you're going to be constructing this table. On the exam, they will not give you this table because in theory, you can do the problem without having to use the table. But when it's kind of like the mean deviation, you can do it without the table, but it's a lot easier to do with, just because it organizes all of your stuff and it's easy to see. So same thing here. They're not going to give you the table because you don't have to use the table, but I highly suggest, and when I say highly, I mean like you definitely should be doing this. So your table is going to contain the outcomes for your game, the probability of getting those outcomes, the net gain, and the product. Because the way these games work is you don't just show up and play. It costs you money to play. So you walk into there's casino games. Obviously, we're not walking into casinos yet, but you pay money when you want to play the game. Or you go outside to one of those traveling fairs, or you go to Laronde and you play a game. You pay money. And then you could win money back, or you could lose money. Or you could just get nothing, but you've still paid that money out. So the net gain is going to be involved with how much money do you lose or gain from getting this outcome. And the product is going to be the product of probability times net gain. The mathematical expectation is we're going to take all of these different numbers and we're going to add them up. And when we add them up, that's our expected value. So if it's 0, the game is fair. If it's positive, that's a game we want to play because on average, we would expect to get positive money, meaning we would win. And if the expected value is negative, then the game is not fair and that's not a game I want to play, because on average, I would be losing money. So there are 3 different cases of problems. We're going to do several of each. You either have to, given a game, determine if it is fair or not fair. Or given that a game is fair, you have to find some sort of missing value, either a bet or the amount of money that you'll win or the number of something. So we're going to do several of each of these examples because, like I said, highly likely that you'll get some sort of situation like this as a 10-point question on the exam. So you want to be able to handle this properly. So we'll have time to do one quick example. There are 20 marbles of the same size in a bag. This is bet, not best. There are 20 marbles of the same size in a bag, 3 red, 7 white, and 10 blue. The bet is $10. You are to draw 1 marble from the bag. If you pull out a red, you win $30. If you pull out a white, you win $15. Blue, you don't get anything. Is this game fair? So we make our little table, and this is how we fill it out. So the outcomes are what I could get from the game. So in the game, I could either get a red marble, a white marble, or a blue marble. So in my outcome column, I'm going to write red, blue, and white. What is the probability of me getting a red? Well, there are 3 red and 20 marbles. So the probability is 3 over 20. The probability of me getting a blue is 10 over 20. And the probability of me getting a white is 7 over 20. Now the net gain, this is the only thing that's a little tricky. The net gain, if we look here, your net gain is what you would win minus your bet. Because although when I pick a red, I get $30, I paid 10 to play the game. So in reality, I'm going to win 30, but I paid 10. So I am walking away $20 in the plus. white. I win $15, but I've paid 10, which means I win $5 in reality. For the blue, it just says I lose my bet, which means I've bet $10, so I don't get anything. So in reality, I've lost $10. So the product is I take the 3/20 times 20, which gives me 3. We're actually going to keep this. Keep the denominators. So always keep these denominators the same and keep the denominators here. So this gives me 60/20. 10/20 times -10 gives me -100/20. 7/20 times 5/20 gives me 35/20. Now my expected value is I take this column and I add it up. So I take 60/20 minus 100/20, because there's a negative, and then plus 35/20. And when I add those up, I get -5/20. So this game is not fair, because if it was fair, this would have been 0. So this game is not fair. It is not favorable to the player, because on average, we would expect to lose money because this is negative. Are there any questions? Okay, so on Thursday, we're going to pick up with the rest of these type of examples, and then we're going to finish up with statistics. On Friday, we will have the review problem period. So we'll talk a little bit more about that on Thursday, like what I expect from you for that. Tomorrow is your SIP prob. Be here, get here early to make sure you sit down and have everything good to go. If you have any questions between now and then, please email me. Now is the time. Don't expect an answer tomorrow morning. So don't email me at 6 o'clock in the morning saying, I have a question. So take the time to study tonight and ask me questions, and then be as prepared as possible for the exam. And if there's nothing else, good luck. Your exam is at 8:30, the same time as this class is at.
Thank you.
Have a good afternoon, everybody. Study hard.
Thank you.
Thank you.
You're welcome. No probability tomorrow.